We on? So just not that these are necessarily relevant to today's lecture, but here are some other structural materials. Here's bulletproof glass, okay? 4 layers. 3 layers are of glass, adhesively bonded in between. It's very important on how you put the adhesive in. You don't want any bubbles in between because you're supposed to be transparent. You don't want to be looking through bubbles. 1 layer is polycarbonate, which is the toughest plastic known. Used to be used just by itself as bulletproof glass, but we have better bullets now. And so it's basically a composite. This is made by the same company that makes, it's called PAS, Protective Armor Systems, okay? It's out in western Massachusetts. And they make a 5 and 1/4 inch version with like 6 layers or something, which goes on the windows of the president's car, okay? And it will stop, the thicker one will stop an RPG. What's an RPG? Rocket-propelled grenade. That's kind of, you know what, it's like the, what do they call the things in Iraq? The shape charges. I should have brought my shape charge. Anyway. I have a shape charge in my office. It's another story. Maybe I'll bring it tomorrow. But anyway, it's a shape charge, and shape charges can typically go through about 3 feet of steel. In fact, I've seen shape charges, I've seen the steel that a shape charge went through 3 feet, because I used to be on the advisory board for the Army Material Command group down at Aberdeen Proving Ground, where they test shape charges and stuff. It's actually interesting to go through armor. Back in the mid 80s, they had developed shape charges to the point where they could go through virtually any armor that was around. And one of my former students working for the Army told me the story. They lined up 3 old tanks on a battlefield, and they shot a shape charge through all 6 layers. You know, one side of armor, second side of armor, second tank, you know, 6 layers of armor. And a armored general tossed his cookies right there on the battlefield when he saw what a shape charge could do. Within a year, there was no shape charge that couldn't be defeated by the improved armor, which was basically ceramic armor. So the shape charges is basically a liquid metal jet of copper that basically just eats right through the steel at the speed of sound, or near the speed of sound. And if you put ceramic in there, copper doesn't react with ceramic, and so it doesn't destroy it. And so now there's all kinds of different armors. I mean, it's proliferating, it's gotten very complex, and they're using supercomputers to model these things. One of the things that they developed for the armor is they had depleted uranium. Basically, it's just a 1/2 inch rod of diameter rod of depleted uranium. It was 36 inches long, and they would fire it at something, and when it hit the surface, the stresses in it as it hit the armor that it's trying to penetrate would essentially get to 300, 400,000 psi, and so most materials would fracture and stuff. So one of the ways to defeat the armor, one was ceramic armor to defeat the shape charge. The other thing to defeat depleted uranium armor, or bullets, or sabots, whatever you want to call them, would be to have an explosive layer on the surface of the armor, so that as soon as it hits the armor, the projectile hits the armor, it would explode, and that would send a shock wave through this thing, which would multiply the stress, and the whole thing would shatter, because you'd have 500 KSI, and it would be above the yield strength of the material because of the shock wave, reverse shock wave. So when I first went there back in the late 80s, they were working on modeling, and they were going to, I don't know if they'd gotten to of actually doing it, but they had 2 sabots. So the one would go in, hit the surface, set off the explosive, and another one would be in the same shell following right behind it at 4,000 feet per second. and it would hit there again because the surface can't explode twice, right? So it would just follow in the hole that the first one had, it's like sending a full back in with blocking for the half back behind you, right? So the armor technology is actually pretty amazing how sophisticated it is. And then what's some other armor stories? Anyway, that's enough armor stories. This is actually a composite material. It actually is a big heavy chunk of steel, and it has on the tip of it brazed. This whole chunk on the end is mostly tungsten carbide, but the very tip is sintered diamond. Okay, so it looks black because it's a bunch of diamond powders that have been sintered together, and it's a double-step braze, which is sort of interesting. We won't go into it, but this is to reclaim asphalt on the highway. When they, in the middle of the night and they're taking the asphalt off the highway and then resurfacing the highway. Well, they have a machine comes along with a bunch of these, and it's just a big auger, and it comes and it breaks up the old asphalt and throws it in the truck, and the truck takes it back to the asphalt plant, remelts it, and recycles the asphalt as new asphalt. But the problem is the tips of these things get a lot of abrasive wear, and the tungsten carbide, which is one of the hardest materials that we have, basically wears out. And you'd like it to last for an 8-hour shift, but they don't always last for an 8-hour shift. Well, someone developed basically a big chunk of tungsten carbide, but the very tip with sintered diamond. And these things would last more than an 8-hour shift, much more. Not much more, but significantly more. And so someone asked me if I would evaluate the technology, because one company was considering investing in buying this other company's technology for the brazing of the sintered diamond. And it's a good technology, but it turns out it wasn't economical because the cost of the sintered diamond was so high that you couldn't just getting another factor of 2 in life was not sufficient. Sintered diamond's not cheap, okay? So that one didn't work out. It worked out technically, but it didn't work out economically. And I guess I got some other things. You've seen this before, but we might talk about it later. And we'll talk about some of these other things. But, so I'll try to bring in some other touchy-feely, so I have to remember to bring in the shape charge tomorrow. So far as that goes.
It says point this way.
Oh, okay. Okay, so we were talking about this thing. Oh, I don't have my pointer. We were talking about the relative cost of a pound saved in a structure over the life of the vehicle. And for ships, it's only 20 cents a pound, or railroads. And the basis is you're going to use these things for 30 years. Automobile, typically you'll get 100,000 miles before it, on average. And it's $2 a pound when you have gasoline at $4 a gallon. Aircraft, it's 100,000 hours, and spacecraft, it's $20,000 a pound in orbit, okay? And one of the things was that SpaceX and some of these other things with the reusable rockets and stuff hope to get the price down to $5,000 or $10,000 a pound in orbit. So when you hear these stories that the aerospace engineers talk about, we're going to colonize the moon, okay? At $5,000 a pound, okay, for what we have to move up there. I mean, just start figuring out what the tickets have to cost, okay? We're going to have graded tickets on people who are lighter weight than others, okay? Anyway, okay, you can also look at these and look at the total market size just in the United States, and you see why automobiles drive things so much and why Toyota taking over a significant fraction of the automotive market was so important. When I was living in Japan in the mid-'80s, 25% of the Japanese industrial economy was based on Toyota and Nissan and the automotive market, okay? Tremendous amount, okay, of their economy. And that's just 30 million cars in the United States. If we go to other countries, well, actually, that's how many vehicles We don't make that many. Do we make that many in the United States? Maybe we do. I can't remember. But in any case, aircraft, Boeing is a very important contributor to our export market and stuff, but it's relatively small compared to other things. And the whole spacecraft industry is also relatively small. Very high-tech materials. You read about all these things in the Wall Street Journal and other popular magazines, and they tell you how wonderful these materials are. And they are very intriguing. But in terms of general economics, let's go to the big bucks, okay? The big bucks are in more mundane materials. One of the interesting things about automobiles, well, we'll get to it in a little bit. Let's go to historically where the United States, and this is a very nonlinear time scale here, but historically where we spent our efforts. Today, the Industrial Revolution of the 1800s to 1950 is over, okay? The red is the industrial sector, and right after World War II, we were in our heyday. We'd bombed out the rest of the world's industrial sectors, and we really were the world's industrial powerhouse. And there's that famous story of whoever it was, American Secretary of State, and the Japanese ambassador says, "Mr. Secretary, Japan would like to export some products," this is in the 1950s, "to the United States." And the US Secretary of State says, "Well, Japan doesn't make anything that we would want." Okay. Well, in 1950 that might have been true, but the Japanese started learning to make steel and ships and automobiles and stuff. But the manufacturing sector, or industrial sector, has decreased. The service sector has increased. The service sector was nothing back in the 1850s to speak of. The big sector back in the 1800s was agriculture. And in fact, in 1800, about 95% of the workforce was engaged in just feeding themselves. Okay? Now, that might have been distribution of food and things, but most of them were out there working on growing crops. And that's why things like in the 1830s, Cyrus McCormick and the wheat harvester or whatever he made, okay, was such an important invention because so many people were out there cutting wheat by hand. The cotton gin by Eli Whitney and stuff, if you remember your ancient history of the Industrial Revolution. That's why those things were important, and that allowed the industrialization, and now we have the growth of the service sector, and then we have this other growing sector of government and welfare transfer payments, which is going to change the whole economic reality of our country and the world. Okay, fabricated cost as a fraction of the cost of structural materials. As much as material scientists like to say, oh, materials are wonderful, materials are a relatively small fraction of the fabricated cost of the material, okay? Raw materials as a percent of the total cost is only 10 or 20% of the actual final manufactured cost of 100% of a product. Materials are small. It turns out design is roughly the same. Fabrication, which is mostly manufacturing, what most people relegate to the mechanical engineers, is roughly double the material cost. Inspection and testing and quality control, which sort of at MIT is over in the Sloan School for quality control, and non-destructive testing is something that we don't even talk about much, okay, is equal to the material cost of the material. And G&A management and stuff is about 10%, and you add all this stuff up and you find you can either lose money or make money depending on how it all fits together. But what that means is that you want to think about, and one of the examples, actually it's referenced in the paper of the materials for the 21st century, that there was a study done by the US Navy. Turns out aircraft carriers gain about 250 tons a year. If you look at the last 50 years, you take the Nimitz class carrier, and they build a new carrier every 1 or 2 years over that period. So we've had 20-some carriers since the Nimitz and all the way up to We actually have a new hull class. I can't remember what the name is, but anyway. But the Nimitz hull design went for about 50 years. And if you look at the weight of the Nimitz, which is in the 60,000 ton class, to whatever the last carriers were, which are up to about 1.5 times that, the average weight gain on an aircraft carrier was 250 tons a year. Most of it, unfortunately, is up in the superstructure or near the top deck, the aircraft deck and things. And that's a problem for stability, okay? So there's a problem with weight gain, and so the Navy was looking at going to a higher strength steel for the hull. They were going to go to an HSLA 60, and they wanted to know what the cost savings might be. Well, it turns out that particular steel might cost you, it's a higher quality plate steel, and it might cost you $2,000 a ton or $1 a pound, okay? I gave you a price of steel before, it's somewhere around 20 to 40 cents a pound, $400 a ton. Well, this stuff's going to be $2,000 a ton. And they did about $1 million study at Newport News Shipbuilding and Dry Dock to find out what the as fabricated cost would be. And they found the as fabricated cost was going to be about $10,000 a ton, or 10 times as much. Well, there's my 10%. Again, I could have done that study for them for $500,000 rather than $1 million, okay? Because the general rule of thumb is, that I've worked out over the years, is about 10% of the cost of a fabricated product is the material cost. So what does that mean for a Ford Taurus that sells, or a Toyota Camry that sells for 25 grand? There's only $2,500 worth of material in that car, okay? However, if you go from steel to aluminum, there is an increase in cost because aluminum is more expensive, and you might add $300 worth of material to the cost of that car. Well, what's the big deal of going to an all-aluminum vehicle? Well, it turns out all these other things for the aluminum can increase that cost by $5,000 or $10,000. Okay, so it's not just going from a $25,000 car to a $25,500 car. It's going from a $25,000 car to a $30,000 car when you go to a all-aluminum vehicle. And that's when, you know, Audi 25 years ago came out with all aluminum structures. But that was for $80,000 vehicles. Okay, now it turns out this 10% figure has some variation. There's two areas I know that I've come across where the cost of the raw material is 30% of the cost of building something, and that's pipelines, like the Keystone pipeline from, you know, the Canadian border down to Texas. The steel pipe is going to be 30% of the cost of digging the hole, putting it in the ground, and everything else. In that case, the material cost is a significant fraction. The other thing is utility transmission towers. You know, these big ugly things you know have 500,000 volt electrical lines on. Yeah.
I wanted to comment real quick, see if you had any comments on like what Ford is doing with their new pickup trucks, where they've got like an aluminum body. Do you have any thoughts on how they're making that work?
Well, first of all, they're using they picked the highest volume vehicle in the world, right? So there's a certain economies of scale that you get that drop the price a little bit. But how they're making it work is they work for 30 years on joining techniques. And the real problem for aluminum is the joining technology. Okay, and I passed around the thing that had steel rivets, and they have things like steel rivets because not everything on that F-150 is aluminum. They have to join it aluminum to steel. And how do you do that without having a serious corrosion problem? Because of the galvanic action and the salt on the roads and things like that. And so there was 30 years worth of development. I mean, I first started seeing it back in the early 90s when I would go visit Detroit, and I would see them in the research labs working on joining techniques and corrosion protection techniques. And it wasn't until 20 years later that they came out with the aluminum F-150. In the early 90s, I used to say that it wasn't we didn't know how to build an all aluminum vehicle. We had had all aluminum Duesenbergs and J.P. Morgan's Pierce Arrow in the 1930s. It's just these were very expensive vehicles. We didn't know how to build at that time a $25,000 Ford Taurus that would sell for $25,000. Well, we still don't know how to build a $30,000 F-150, but we do know how to build a $35,000 F-150. We've brought the fabrication cost down. If I go back to the previous slide, we amortized a lot of the design and engineering over the largest vehicle production lot in the world. This big thing here is what they really drove to bring the cost down. Okay, so it's these two things in here, and they did some things in here. Plus, to a certain extent, they're hoping to keep their market share, and they may have taken a hit in here to a certain extent. But in fact, the whole raw material sector, the aluminum companies were never quite ready to invest in the production capacity that would be needed for the sheet material until one of the automotive companies was going to commit to a large vehicle platform. And when they did that, a lot of what you see in the growth in the aluminum business in the last 2 or 3 years is because Ford made the commitment to build an all aluminum high production vehicle. You know, the amount of aluminum Audi used, you know, it could be important to an aluminum company, but it's not that important. It's not going to change their product mix percentages. But when you go to a Ford F-150 with 800,000 vehicles a year, it makes a difference, okay? And in fact, there are problems in that Ford didn't want to do it if there was only one aluminum supplier for it. That's another thing. In the $600 billion automotive industry, GM and Ford will not commit to using a new material if there's only one supplier. So if you got a wonderful material, monopolistic position, they'll thumb their nose at you because they know what you're going to do to them if you got a monopoly hold on them and they design it into a new vehicle. Okay, all of a sudden, oh, our costs have gone up. You know, only to them it's all their profit. You know, they'll steal $10 billion worth of profit. So they want to have multiple suppliers, and this is another externality, if you will. Okay, in terms of the automotive business. The other thing that GM is very, very careful of is avoiding lawsuits. I mean, there are people out there who will essentially try to get something into GM and claim that GM made a commitment, and then GM will say, no, we didn't make a commitment, and then they'll sue GM for billions of dollars because they restraint of trade or whatever they call it. And GM is very gun shy of that because they've had some very expensive lawsuits. Okay. Other questions? So pipelines, transmission towers. I'm just finished up working on a project that was for 1 million tons of steel for transmission towers. $1.3 billion purchase of the steel to build the transmission tower. So that's $1,300 a ton for galvanized steel. Automotive and aircraft, it's about 10%. Spacecraft, it may be down around 2%. And semiconductors, well, obviously that's not a structural material, and your actual material cost is relatively low as far as that goes. Materials as a percent of the total manufacturing. Yes?
How can the aircraft or spacecraft be like 2%? Surely the materials have to be like really structural, you know, to go through the atmosphere and also withstand space junk.
Because it's all engineering and fancy composites. I mean, this is, as fabricated, this is $20,000 a pound material. Okay, that's what it costs. Or actually, this material only costs $12,000 a pound. Okay, as fabricated into the structure. But the actual material weight in the structure, it's only 1 or 2. The cost of material is only 2% of that, even though they're using carbon fiber composites and things like that. The material cost, which For an automobile, it would be 10% of the cost, but for a spacecraft, and a lot of that is the inspection and stuff goes way up, okay? Think of the Hubble telescope, okay? For a Hubble telescope, and I use that as an example because if you remember, the Hubble telescope had a few design problems on the mirrors, and they had a $2 billion project that all of a sudden could have been junk if it hadn't been for Lincoln Lab developing a military technology to control distortion, or to compute away the distortions of the atmosphere. One of the reasons for putting the Hubble telescope up in space was to get rid of the atmospheric distortions. Well, they put it up there and they find they had distortions in their mirror. Well, it turns out we'll never build another Hubble telescope to do optical imaging in space, because of places like MIT and Lincoln Lab, they can shoot a laser beam through the atmosphere, measure the distortion of the laser beam going through the air. I mean, so it may be shooting down from I don't know if it's shooting up or down, okay, but there's a satellite up there, and it's measuring the distortion of the beam going through the atmosphere. And then they back calculate all that, and they can now take pictures from Earth through the atmosphere that are just as accurate as the Hubble telescope, because they are doing computer correction for the distortions of the laser beam going through the air. So we'll never need to build another Hubble telescope, okay? But why did they do that? Well, if you want to read the president's golf card, okay, and what his score is from 100 miles in space, you've got it correct, okay? Unless he uses really big golf carts, okay. Okay. See if he's cheating on his golf score. Okay. Does that answer your question? Okay. What?
I have a question about like when you would use steel for transmission towers versus wood.
Versus wood?
Yeah.
Oh,
so
okay.
A lot of like towers that I see are like all the same wood. Everything seems very uniform.
He's not talking about.
I'm not talking. Yeah, I'm not talking about the ones that are taking 10,000 volts down the street to a transformer. I'm talking about the $500,000 volt transmission towers that are about 100 feet tall, 150 feet tall. These are the big utility transmission towers. Okay. The other ones they call distribution towers. Okay. They actually have a hierarchy of terms. The transmission towers are when you're transporting 500 to 1,000 miles. And then the distribution is when you're trying to do 10 miles down the road, okay, from some power transformer base. And actually, the wood is now, when I was a kid, the wood would last 30 or 40 years. Now they got treatments for the wood, and it never rots in 100 years, okay? So far as that goes, the wood stuff has gotten better, but they're still ugly, and if you can afford it, you'd rather bury it in the ground and have a neighborhood that doesn't have a bunch of wires all over everywhere, okay? There's actually a famous old picture of New York City with all the telephone wires. I don't know if you've ever seen that in around 1900 or whatever. It's just nothing but telephone wires in the street. Okay, other questions? Oh. Okay, so we went through that and hopefully clarified that. If we want to talk about materials as a percent of the total manufactured cost, whether it's 10% or 20%, if steel costs $400 a pound, you can actually afford to make ships and railroads out of it, but you barely can. And these are the materials that are cheap enough to make ships or railroad cars. If you're willing to go to 20%, we do make aluminum railroad cars, okay, because they're lighter weight and you're pulling all that weight around, okay? Automobiles at 10%, it's steel. At 20%, you can use aluminum and plastics, although you have a hard time using some of the plastics, but we'll talk about that in a little bit. They have built the Bmw i3 and i7, okay, out of graphite fiber, but we can talk about whether that's how they did that, okay? And actually that was a student's presentation in this class, was the Bmw i3. But he had studied this for some time. I don't know if he was a BMW employee. He was an LGO student, as I remember. Anyway, but he explained how they could beat this thing. But it's also You start loading up the i3 and it's a $60,000 vehicle, and the i7 is a $100,000 vehicle. So it's like the all aluminum Audi, okay? The first ones that come in are on the high end of the scale, okay? Aircraft aluminum for years and years, and now we're switching over to composites. That's not what limited the composites. The thing that limited the composites was the fabricability, okay? Could they repair them and things like that, okay? And the American Airlines jet that landed in Brooklyn or whatever when it took off out of Kennedy or whatever, that was basically they had repaired the empennage. They had problems in production, and they repaired the empennage. And that was actually a student's presentation. Was American Airlines, I can't remember the flight, was it due to pilot error or was it due to the repair, the composite repair? And people are still on both sides of that, okay? But that's another project, a student presentation. Spacecraft, you can certainly afford composites, and you can even afford some refractory metals like beryllium that are just horrendously expensive. And what I have down here, but it also depends on your economic class. Some people in the Ozarks will build their houses out of wood, and other people in the Hamptons will build them out of whatever they care about. Or Martha's Vineyard is the big example right now, where people are building these $20 million mega mansions on Martha's Vineyard. So one of the people who's I like to quote is Robert Sprague, who was materials manager for GE aircraft engines in Cincinnati, and he said, whenever you first hear about the properties of a new material, write it down, because those are the best properties the material will ever have, okay? He said that 30 or 40 years ago, and he said that with a lot of experience. And Jim Williams, who replaced him, he was Dean of Engineering at Ohio State, or he went back there after a while, but he replaced Sprague, and he had a corollary: whenever you first hear about the cost of a new material, write it down, because that's the lowest cost it will ever have. New materials always their properties always degrade with time, and their cost always increases with time. So be careful about claims for new materials. Another thing that people do with new materials is they will be very careful about how they phrase the properties. And the example I like to give, there was a Professor Gary Wennick, who was an assistant professor in this department. He left before tenure ever came. He was really a chemist, but he worked on polymers, and this was back 25, 30 years ago when electrically conductive polymers were sort of a new thing, okay? And he was giving a talk in the Chipman room about some of his research on electrically conductive polymers, and this, at the time, the polymer was polyacetylene. And ordinarily, polymers are covalently bonded, and there's no free electrons, and that's why they're excellent insulators. Polyacetylene has a bunch of double bonds, okay? And so, properly doped, it can have some free electrons, and so it's electrically conductive. And he was pointing out that the specific electrical resistivity of this polyacetylene was better than that of copper. And therefore, things like big rotor generators and rotating machinery and motors and things would all be using polyacetylene or other conductive polymers in the future. And I thought, wow, that's pretty impressive. Until the next morning, I was shaving, I almost cut myself as all of a sudden I realized, wait a second. Today, aluminum has a better specific electrical conductivity than copper. But we still wind those motors and those big generators out of copper. Why? Even though it's spinning at a very high rate of speed, we need the lowest electrical resistivity, okay? We don't need the lowest specific electrical resistivity. What was he doing? He was dividing by the density, and because polymers have a low density, their specific electrical resistivity was better than copper, but that was not the figure of merit for rotating equipment. It was the lowest electrical conductivity, and the only thing that's better, anybody know the one element on the periodic table that is silver? And why don't we use silver? because it's 100 times more expensive than copper, okay? So there is a cost consideration, but it's a factor of 100. In fact, during World War II, at Oak Ridge National Lab, they used big magnets to separate the uranium. Okay, they had these basically a great big mass spec, and they would separate the uranium to get the fissile uranium from the non-fissile uranium isotopes. What, U-238's fissile or U-235? I can't remember. Anyway, they just had a great big mass spec, and they had all the uranium hexafluoride vapors running around in a circle, and they would separate out the lighter ones. And it turns out copper was very, very short supply during World War II, so they wound their magnets out of silver from the U.S. Mint in Philadelphia. And after the war, they had to return the silver to the U.S. Mint, okay? But nothing had happened to it other than fabricate it into wire. But silver is better. Yes?
I don't really believe this.
What? What don't you believe about it? You can disbelieve it. It's not my quote. Oh, go ahead.
Like,
I'm just propagating it.
with silicon, which is what I work with,
Yeah.
it's definitely gotten better properties and it's become cheaper.
Is it a structural material?
Is it?
It's a functional material.
It's a functional material. That's true.
They're talking about structural materials that go in engines. Okay.
So
like-
for specific material.
Right.
Type.
And you have to recognize they're coming from the jet engine business.
Right.
And people will come in with fancy composites or some new metal alloy that's supposed to be higher temperature or whatever. And things were always ended up never quite having the properties they wanted. You're talking about something still on the learning curve where we're seeing tenfold reductions in price every 5 years or whatever. That's sort of a different maturity. These are further down the maturity curve, okay? So no, it's not true for every material, but I mean there's some wisdom to what they say, certainly in their industry, okay?
I think there's even with like new semiconductor materials, everyone gets really excited about something new.
Yeah,
Like they'll still have, right now perovskites are really big in semiconductors.
yep,
Especially for solar, and they degrade in like 1,000 hours.
yeah.
So it's the same.
Well, that was the problem with polyacetylene electrical conductors, okay? They oxidized in the air within minutes. Okay, so as long as you want to run your generator in an argon atmosphere or a vacuum, it's fine, okay? So they don't always mention about some of the Achilles heels that some of these things have. So the perovskites are a good example, okay? They don't have the stability. Well, if someone comes along with a breakthrough to improve that stability, then they may take over, okay? They've got certain beneficial properties. But these guys, I mean, Jim Williams he coined the term boutique materials, okay? And the reason he called them boutique is some of these materials, well, there's going to be a market for these things of 1,000 pounds a year. And who's going to make it? What company is going to invest in some super duper material if they're only going to sell 1,000 pounds a year? There's a market volume issue here too. Not just what you can make in a laboratory. And I guess part of the point here is people will claim all kinds of things for what they can make in a laboratory, and they can be very interesting from a scientific point of view. From an engineering point of view, it's crap.
Are
Okay?
there any like statistics on the number of new material or composites created versus how many make it to market and how
Well,
many 1,000 pounds make it?
not specifically for materials, but that I know of. But in general, 1 out of 20 companies will be successful. Okay, 19 will fail for every one that's successful. The other thing about materials, which is not really something I came up with, but most people credit a paper I wrote in 1995 that I didn't quote who I had heard it from, but it takes 20 years to bring a new material to market. And I gave you a paper on bringing new materials to market, that 1995 paper in Technology Review. At the time, it was the most requested article ever in Technology Review because everybody was excited about new materials. And in there, I talked about the problems of bringing new materials to market, which most people, I mean, that's what these guys are saying. I actually wrote an article about it, and you can read about refrigerators, which Brian will talk about later this week when I'm gone. I'll be lecturing tomorrow. You're lecturing Wednesday, and then Dr. Belmar will be Thursday. We're going to give you Friday off. It's an MIT holiday, okay? It's not that we're generous, it's just that it's an MIT holiday. Anyway, you have to be, the point here really is not necessarily what they say about their class of materials. It's really about be very, very cautious when people start making claims about new materials. Yes?
Just to add, I work in batteries, and I think both of these apply across every new battery material that ever gets invented. Everyone just thinks they have the best energy density, the best power.
Well, how are you going to raise your money unless you've got the best, right?
Right.
And so the people who are saying this, well, I'll give you an example that really sort of bugs me no end because I'm a steel guy, okay? There was a guy in chemical engineering, graduated from MIT, went to work for US Steel, and he learned that molten steel is a universal solvent. Just like water is a universal solvent for lots of things, you can dissolve lots of things in water. Molten iron is a wonderful high temperature universal solvent. So he decided he was going to throw a lot of the environmental waste into steel, and it would just dissolve, and then we could sell the steel. And he gave this idea to US Steel, and the people at US Steel were not stupid, okay? They looked at it and said, no, if you want it, you can have the patent, okay? Well, that did not deter him, okay? He patented it. He came to MIT. He got together with the head of our technology licensing office, a guy named John Preston, and they started marketing this as the solution to the world's pollution problems. We could throw everything into a bath of molten steel. And they called it Liquid Metal Technologies, okay? They raised $130 million. Overnight, these two guys were worth $25 million apiece, okay? When Vice President Gore was talking at MIT at Kresge Auditorium, John Preston, head of the Technology Licensing Office, was in charge of putting together the program of panelists about new technologies. Who did he put on as one of the four panelists other than Chris, whatever his name was? I can't remember, the guy who had come up with the patent. Don Satterway, and I said, hey, wait a second, it seems like a little conflict of interest here, okay? You're using your position at MIT to promote. We actually called up the Vice President of Research, said, hey, there's a little conflict of interest here. And MIT, in their great wisdom and high integrity, said, oh, MIT's got a piece of this action, so we don't think there's a problem. Okay? This is a true story, folks. So Satterway and I said, okay, we've got the same types of crooks in the administration. There were a few problems with that. There's an element that will destroy steel refractories called sodium, okay? Do you think there's any sodium in most of the waste streams? If you want to throw garbage, I mean, there's sodium all over, right? It's a couple of % of the ocean, okay? And it's in all kinds of other things. And you would destroy all your steel making technology. They built a plant down south of here, and there were several very distinguished faculty members, department heads and others, who were on the board of directors and had pieces of this company. And I was just deathly afraid that someday this was going to come and MIT is going to get a big black eye when all the chickens came home to roost because of these types of things. People were saying, this is wonderful. I was given a talk, this was back when we had what's called LFM before LGO, and someone actually asked me before class what I thought of liquid metal technologies, because it was all over the Wall Street Journal, this wonderful MIT technology and stuff. And I said, I can't remember how I phrased it, but I basically did not say anything complimentary about it. And it turns out, the student was asking because his father was an investor and was thinking about investing in it. I said, don't. I said, this is pure crap, okay? If they knew anything about steel technology. The other thing, there's another element called chlorine, okay? And you know what happens when you put chlorine into a steel furnace? you get phosgene gas, COCl2. Phosgene gas is one of the gases they used in World War I to gas people. Okay, it's toxic. So Chris and John knew nothing about this. These MIT professors, okay, who were making some money off this new startup, I don't know if they knew anything about it or not, and I just laid low. I thought, I tried to say some things about it. Well, anyway, when I was lecturing over at Sloan, they said, I guess it came up because they were reading the Wall Street Journal, and there's a famous quote that I made over there. I said, well, once you read about it in the Wall Street Journal, it's no longer news, okay? So don't do your investing based on what you read in the Wall Street Journal, because all the other investors are reading that same thing that same day. But they were claiming they were going to get a $30 million contract from the Department of Energy to get rid of radioactive waste. Wait a second, you're going to throw radioactive waste into a big steel bath and somehow it's going to transmute those nuclei into a non-radioactive form? I mean, this is new science here, folks. But they were getting $30 million from your government and my government, part of our tax money. And this is just, how bad is this science, right? Well, what finally happened was about 3 years later, they were indicted. Okay? And fortunately, MIT's name was not in the article on the newspaper. It didn't list MIT as the startup. Okay? So, some of these things get really, really nasty. Okay? Be careful. Try to go find somebody who knows what they're talking about.